Everybody and good afternoon. Today I'm going to present a little bit about bone screw fixation in general and in particular patient-specific spinal bone screw fixation in a homogeneous and voxel-based material finite element analysis. My name is Matin. I'm a postdoctoral researcher here in this department. So I'm going to start a little bit with the importance of bone screw fixation. What do exactly expect from bone screws? One would say the attachment of two fractured bone parts. The other one would be the transferring load from one specific part to the other part, as we can see in spinal fusion systems, and also maybe replacing the main tissue, as we can see in dental implants. But all we can expect from bone screws is just summarized in one word, which is stability, or in other words, fixation. There are a wide variety of bone screw evaluation tests. Among them, pullout test is a very well-known test that normally researchers and surgeons are interested in. But in pullout test, what do we do exactly? We're pulling out the bone screw from the block test or bone, and then we find out about the relationship between force and displacement of the screw out of the block test. So we have the relationship between the force and displacement. So we have the pull-out stiffness, we have the maximum pull-out force and displacement at this point, and we have energy dissipation or external work. So the energy dissipation and external work is very important because not only it includes the elastic information about the pull-out test, but also includes the fracture point or plastic deformation. So these are the parameters that we can actually incorporate it in validation and simulations. So when we talk about the simulations in finite element analysis, then we need to consider some complexities like geometrical complexities, material complexities, and another important one is the interaction complexities. So first, if we want to have the most complex geometry, then we have the microcity images. Then we segment it, and then we input it into the commercial finite element softwares, and then we have micro finite element. But we cannot do it in patient-specific analysis because due to high exposure of X-rays. So we go back to the conventional CT scan images, and then we segment it, and then material map based on the voxel-based, and then we call it as a heterogeneous finite element. Or another way, we use homogeneous material, so we use homogeneous finite element. So it's very simple, low cost of calculation, and most the researchers use this. So in our study, we use two models. First, voxel-based material properties assigned based on this table. And then we applied the pull-out test to the head of the screw. So placed it in an olive approach. So the screw actually goes through the body of the vertebra. And then we use another model, which is homogeneous material. We used the average Hounsfield unit of two-fold diameter of the screw. And then assign it to the whole body of the vertebra. So we call it material reference volume. And then we compared these two together. So in the comparison, actually, if we have Hounsfield unit less than 100, the standard deviation, I mean, then we have less than 5% error between the stiffness and the force measured in the simulation. So I could say that this can save a lot of calculation costs at the same time, but the accuracy and the error is less than 5% in the materials that the Hounsfield unit is less than 100. So when we talk about the simulation, it's not only about the complexity of materials and geometry, but also is about the interface, or in other words, we call it interference. Because when we want to consider the stress distribution, then we need to go from the bone to the implant. So the material property drastically changed and then we need to consider these interfaces. So also there are other, let's say, considerations that we should take into account. For example, when we want to insert a bone into the screw, insert a screw into the bone, then we need a bone drilling. And then we have a pilot hole preparation. So in bone drilling, due to a high friction between the drill bit and the bone, we have excessive heat generated, and then the temperature of the bone rises, and maybe we could actually see some osteonecrosis there, and it can affect the bone healing and remodeling. So we assume that these parameters are as optimum as possible. And then we have pilot hole preparation, like the pilot hole size or pilot hole diameter. And then we have bone screw insertion. So the screw insertion means that you put the screw inside a pilot hole that they have different sizes. So the undersizing between the screw and the pilot hole does matter in simulations. So in one study, we attempt to find out about the optimum pilot hole diameter. So if the pilot hole diameter increases, the fixation stability decreases. And in other hand, if we decrease the pilot hole diameter, then the applying damage to the surrounding of the bone increases. So we need an optimum point here. And in this study, we actually tried to find out about this optimum point. So in a pullout test, alongside the other experimental test, we found out that the 5.5 millimeter is the optimum pilot hole diameter here. And it's exactly 1 millimeter less than the outer diameter of the screw. So here we only used 4 pilot hole diameter, but we could actually make it more. So also when we talk about screw insertion, so we are talking about the surfaces between the screw and the bone. So we assign surface and surface hard contact in the software, and then we assign coefficient of friction. So in one attempt, we tried to have a sensitivity analysis on the coefficient of friction, and we found out that a slight increase can occur in the pull-out force, but it has not many significant effects. So it seems that I'm running out of time. So also another thing is that is very important is that the pre-stresses that induced or developed in the phase of inserting the screw inside the bone. So in one attempt, also in 2021, we actually put some let's say displacement at the interface of the screw and bone, and then we transferred the pre-stresses from insertion process into the pull-out process. And then we found out that here, by actually changing from the free stress model to pre-stress model, we could actually enhance the validation. Also, this could happen in different materials like low-density polyurethane, low-density polyurethane, high-density, and high-density polyethylene. So, as a conclusion, different types of complexity affect the accuracy of computational modeling in terms of finite element analysis. Also, there are also other complexities that can be taken into account. I also took some of those in my poster presentation. It would be welcome to come and talk about it. Thank you so much.